Welcome back to 128A after the midterm exam. I'm not going to talk much about the exam. I assume in section today you will, and you'll get them back. So sorry about the B courses thing. I know some of you never got your score. I didn't. It's a great idea to post them there. I just didn't think of it. My plan was to post it on Tuesday, but then I told the GSIs late Friday, why don't you post it on B courses? And I think some of them did and some did not. Maybe they didn't bring the exam home or something. So don't give them too hard time about that. At least you all get it back today. You know the solutions are online, and you know the scores, etc. And maybe just in terms of grading, you all know the policy. Many of you did really well, and I was happy to see that. Others of you, if you feel that even reading the solutions, you struggle with this, the problem is going to be, the understanding. You might want to have to review all this material in time for the final. In terms of all questions like, oh, I did not as good as I hoped, can I still get, a certain grade? The answer is almost always yes, because of the grading policy. Namely, that automatically we'll count the final instead of the midterm. So that's not the key. The key here is that this was an indication of how you're doing and how is it going. The exam was not super easy, but not, I think, super hard either. Fairly typical of the prior exams in this course. So see it as a good learning opportunity. If you did great, that's a great indication. Otherwise, you might have to study a little bit more in time for the final. And grading questions, of course, you check with your GSI today if there are any issues about that. But we try to be very consistent when we grade. Here's the plan for the rest of the class, actually. I actually never covered this, which will be due. Remember, we have a homework due. I guess it feels far away from now, but it's 2 weeks. But it's right after spring break, so we got to cover it now. Just pretend like spring break doesn't exist, because we don't really want you. You guys should relax during spring break. So finish up all the homework today, and it's going to be, of course, on what we missed last time, 4.9, and these two sections as well. So hopefully today in section they maybe spend a little bit of time talking about the exam, then you'll get to the homework. I want to mention too, I did in an announcement that I posted program assignment 3, and I postponed the date. I had originally planned to have it due this date, and it just doesn't work. No. I had planned to have it due on the 8th of August, but that doesn't quite work out with the material, because you won't learn stuff you need until the Tuesday after spring break. So I postponed now, so the programming assignment 3 is going to be due on April 15th. And it's posted, and it's actually, we can't really even talk about it yet, because it's on this new material that we'll start on today. So it's in the advance. If you want to read ahead, of course, over spring break, definitely you can start. If you want to work ahead on spring break, you can do it, but we'll come back to that more later. And of course, the big part I told you before, we have 2 huge sections. Maybe the biggest part of the whole course, or in numerical analysis in general, is solving differential equations. And we're going to solve one particular type of differential equations, initial value problems. That's chapter 5. It's a huge part. And just for the rest of the course, there's going to be something that I think some of you will find maybe easier and more familiar, namely some linear algebra at the end. That's the whole plan. And yeah, so I guess I have 3 sections to cover today, but it's OK. We'll leak it a little bit into Thursday, and we'll be fine. Any general questions? But the exam, maybe something technical that I could answer and not your GSIs. All right, so you're ready to get started? Here's the very last. It would be nice if we really finished chapter 4 and we could start a new thing now with chapter 5, but we didn't. We left one last section at the end. And it's actually just 3 or 4 pages in the book. It's a few nice tricks, and it's kind of important. So let's look a little bit about it. The idea here is that you want to compute integrals that are improper. And you might, if you feel uncertain, you might want to review your Math 1b stuff here. First of all, what is an improper integral? Well, there are 2 types. One is that the function is not bounded. So as you know, you can integrate a function like, for example, 1 over t squared. It goes to infinity as you go to 0, but perhaps you can integrate it, right? And it's something we looked at, whether it was possible or not. And let's see, what did we figure out? We figured out that t squared was not possible, but 1 over square root of t you can integrate from 0 to 1. And you remember why? Because it was kind of this amazing, kind of almost counterintuitive in when you take calculus, that you have a function going to infinity, you would think that the area under it also has to go to infinity. But no, not necessarily so. It might very well, and I think, again, 1 over t squared would, but not 1 over square root of t. So that's kind of amazing that that works out. So how can you do that numerically? Can you imagine our methods operating on these functions? Can you imagine Simpson's method trying to integrate, for example, 1 over square root of x from 0 to 1? What would it do? Simpson's method with let's say, 5 points from 0 to 1, right? Well, obviously, it's going to crash immediately, because you can't even, you put the point at 0 here, it's not evaluable, so it really doesn't work, okay? Now, you could argue, why don't we just try to avoid the 0 and do, for example, Gaussian quadrature, right? And that would work, but the convergence properties are all bad because all our estimates are based on forced derivatives, and they all blow up. So our estimates will tell us that the error could be infinitely large. And although, of course, it would be a finite number, it would be bad. So we cannot really apply our methods directly on that. There's, by the way, another type of improper integral, kind of when you mirror this around and not necessarily have something that goes to infinity, but you have something that goes to 0 at infinity, but your integration bounds are infinite. So for example, the integral from 1 to infinity of, now we got to do 1 over x squared. This actually has a finite error. And then, again, that's a paradox. How can you integrate something to infinity? And it's always positive, right? 1 over x squared is positive, and still we integrate all the way to infinity, and magically there it has a finite error. So how do we do that numerically? Can you imagine that's a problem too for our, how would you do a composite Simpson on the integral from 1 to infinity? I mean, in math, we like to take limits and infinite and convergent infinite sequences and series, right? You can't do that in numeric. You have to stop sometime. And indeed, the very first thing you might think of is, why don't we just go till from 1 to 1,000? I mean, after all, the function is supposed to converge, right, and die out. That might be OK. And indeed, you could do that. But there are some nicer tricks. And here's a particularly nice trick to handle these things. So these slides, or actually this and the next, is describe the whole thing, and then I'll show it. But it's easiest shown with an example. But it's a little bit more general. So you want to integrate something. If you start with just something like this, 1 over x minus a to the p, from a to p, it's really what I have here with p equals 1/2. And I guess I set a and b to 0 and 1. And that's it, right? And I set a equals to 0. So I just generalized a little bit. You have a singularity at a, and you're integrating from a to b. So you could say that you have a singularity at the left endpoint here. And we did show in calculus, like I said here, that p greater than 1 is not going to work, or equal to 1 is not going to work either. So p has to be between 0 and 1 for this to be interesting. And then you can really just integrate it, and here's the answer. So that's what we did in calculus. Why do we need numerics? Well, this was boring, right? So clearly, the answer is, don't use numerics for this. Just use calculus, right? So to turn this into something more interesting numerically is that you have something that you don't know how to do with calculus, but still has this type of issue. And one general class of problem would be when you have some function g that is well-behaved, no singularities or anything, and then you have this particular singularity in the denominator. That's more interesting. You can't do it with calculus. Maybe we can apply it. And here's a nice trick where you will be able to actually do a little bit with analytic calculus and a little bit numerically, and you can calculate these things using numerical methods. So we're going to consider the special case that we go from a to b. We have a singularity at the left endpoint a, and there is an arbitrary g here, but it's well behaved. In this case, we say it's just continuous. Okay? And p, of course, still has to be between 0 and 1, unless g is special, but we're not going to assume that. Here's the trick. You want to kind of try to cancel out this singularity with as many terms as you can in the Taylor expansion of your g here. Okay? So you take this, and by the way, there are more requirements on g, because here I obviously assume that you have 4 derivatives of g. So g is well behaved. So you figure out the 4th Taylor polynomial of this function, little g, and then what? Well, the next slide tells you what. Now you do this little trick. You want to integrate g over f of x, which is g over the singularity, right? And the trick is you subtract away the Taylor polynomial, and you add it back in. Clearly, I didn't do anything, right? Still the same integral. But now you group them in the following way. You do gx minus p4, and we'll see what we do about this thing. But here we have just a Taylor polynomial divided by a singularity. What's the good news about this thing here? It's kind of just a polynomial, right? Although it has this division. But it's going to be monomial terms that are trivial to integrate by hand. We know how to do it. This is still difficult. It's still difficult because there's a g that we don't know how to handle. But since you subtracted out a bunch of, in fact, the first 4 terms of the Taylor expansion, turns out that this function will be well behaved up until at least fourth order that you need for composite Simpson method. So this is the trick. Here on the slide, I tell you how to integrate this last term exactly. I don't think you need this here at all. You just write it up and do it. This is just telling you that you know how to integrate this thing. Again, it's a Taylor polynomial. Remember, it's about the point A. So it's really a constant plus a constant times x minus a plus a constant times x minus a squared, etc. Right? Pretend a is equal to 0. You'll see how easy it is to integrate this. And you can write an expression. I would not do it myself. I would just figure it out as you need it. What's more interesting is this other part, g of x minus p4 of x. And you have to think a little bit about it, because clearly you can't even plug in a. So we still have a slight issue. You cannot plug in a, because clearly gx minus p4 at a is 0, right? Because the p4 is the 4th Taylor polynomial. So in particular, the constant is right. But it's many more degrees. Actually, 4 derivatives are matching. And then you would do 0 divided by 0. So I can't even plug in a. So it's unclear what to do about this thing here. But as it turns out, if you just define that it's equal to 0, and you can show, of course, by doing various limits. This is a typical Math 1a exercise, where you show that this is actually a function that makes sense. You cannot evaluate it at a point, but you define it to be something. You check that the limits are the same, and it works out. So if you just pretend this little g should be called big G, I think. Really bad that I have little g there and little g there. Wrong. I'll fix it. You define a new function, big G, that is really just this expression here, but you set it to 0, so if you have to plug in that. Okay? And then you can make a little argument that since all these derivatives agree, this big G here, this should be a big G, has, well, as I said, it's continuous. It's fairly easy to show. You can see easily that you will at least have a continuity. This function will go to 0. But you can keep on taking derivatives with L'Hopital's rule and see that it actually has 4 continuous derivatives. Okay? What does that mean? Then it might be bad after that. We're subtracting out these 4, and then anything could happen after that. But that's all we need for Simpson. In fact, if you want to do trapezoidal on this, you would only have to go, you wouldn't need to go all the way up to 4. You could just go up to the second. So it's kind of in a loose hand-waving way. You subtract away the polynomial parts of your function. Remember, e to the x is kind of any nice function can be written as an infinite sequence of polynomials, right? And you take the first few of them and do them manually to divide out this singularity x minus a to the p. And then the rest of them will be just a tail that you do numerically using this method. Okay? That's the whole plan. You'll see with an example, but this is the whole plan. And if we'll come to this later. Let me show you an example. A typical example would look like this. This is not a typical example because it's boring, and you would just use calculus immediately. But maybe a more interesting case would be when you have integral from 0 to 1 of sine x over x to the 1/4. Okay? And I don't think we know how to do this. I forgot all the 1b stuff. It certainly doesn't look, maybe. You never know what integrals are. I guess you ask Wolfram alpha nowadays. It doesn't look like those things we knew. But you never know with integration by parts what you could play with. So let's just pretend we don't know how to do it, and we want to do this numerically. And you should, of course, immediately look at this. It's going to be a big part. When you do the homeworks on this section, you know that something is weird, right? But I know that, especially in Math 1b, it was always the first. I tell the student, figure out if it's an improper integral or not before you start doing stuff, right? And it's the same is true here, that before you start doing anything, you see what's going on here. And of course, it fits this pattern perfectly, right? Because I'm integrating from a to b, which is 0 to 1, and I have a singularity at the left endpoint, 0. Okay? You can also go on and check the p-value here that is between 0 and 1, so it makes sense. And you have a g here that is well behaved, in the sense that you have as many derivatives as you like. So it fits this framework perfectly of how I set it up here. So we can do this, and what do we do? Well, we start off by saying compute the 4th Taylor polynomial of the little g of x, the thing in the numerator, and then we subtract it away and do this little trick. So let's start by the Taylor polynomial. That's easy. So P4 of x is really just x minus x cubed 6, OK? So the trick now again is that if you wish, you could see that you replace the sign. We don't want to just replace. I mean, to a first approximation, you could just replace that, right? But we want better. But just in terms of how to think of this, suppose you say that, well, this is approximately equal to that, right? So you could just plug it in and you're done. OK? But this method, of course, would say integrating all the way to 1. This is not that accurate all the way up to 1. So we're going to do better. And what we're going to do is that we're just going to plug it in, but we're also going to see what the remainder is and do that numerically. OK? So the trick is here to plug it in. And let's first look at these two integrals. I guess I'm doing the trick on the top here. But I'm going to take my sine x and subtract out this polynomial. I claim that's a well-behaved function, even when dividing by the singularity. And then I'm going to do exactly what I said, namely just take this divided by the singularity and add to it. And of course, adding those together gives us what we started with. I just subtracted the polynomial, put that to one part, and then I added it back again. Okay? So let's look at these two components. So the easy one is just this polynomial itself divided by the singularity. Okay? And as I said, this is easy. You just do it. To write it out, you can see that. And you might think that this was a little too easy to be the case. But as I said, even if you have x minus 1 here, or a, this is a Taylor polynomial about a. So it will always be very easy to just divide out those terms. Okay? Minus x to the, I guess we had 11 quarters here divided by 6. And this is routine to integrate. In fact, it becomes, it goes a little bit too far. That's a good spot. Well, whatever tricks you do, so here you could use the expression in the slide here at the bottom, right? But why, when you can just figure it out by hand? If you remember your integration rules for primitive functions, you get something like this, and this becomes 15 quarters for 7 minus. And this is something like, and I'm going to need a lot of digits here to make this interesting. 5279A4, okay, whatever it is. And here, let's now see the big picture here. So one thing to do is to just say, wow, this is actually not too bad. And the answer is, that's true. And you could actually go even further, right? And it's nothing different from what we did before. You can approximate this function well by a Taylor polynomial. And if you just replace it, you're making an error, but maybe you're happy. And you'll see when I actually do the correction that this is not too bad. This is the significant part of your integral. And you got it by saying, I don't know how to integrate. It's actually one of the reasons Taylor polynomials, and you remember the end of Math 1b, that you solve differential equations using infinite expansions? That was the whole point. We like polynomials. We know how to integrate and solve polynomials. So if we don't like a function, replace it by a polynomial, right? And the only issue is that we cut it off. So again, this part of it was kind of trivial. But now we're going to be a little bit more greedy and say, hey, there's an error. We don't know what the error is. Let's try to be smart here. And I've done the right integral. But let's go back to look at this gx minus the polynomial and see what happens there. So first, we define this capital X, g of x, sorry, to be really the numerator subtracting out this polynomial divided by the singularity. OK? So the thing you want to integrate, only you had this issue that you can't plug in a. So if x is equal to 0, you set it to 0. Otherwise, you set it to this. And now, as we claim on the slide, here, you can argue that this function is well-behaved enough for Simpson, which means that you can just run Simpson on it. Composite Simpson on g of x. And this gives you, well, let's do it over here. Now you're doing integral from 0 to 1 of sine x, or let's say just replace it by gx. And it's approximately equal to 0.25 over 3, and just Simpson, plus 4g of 0.25, plus 2g of 0.5, 2 more, plus 4g of 0.75 plus g of 1. And this, of course, you just evaluate, right? Except this guy, you get the special case, right? You can't plug in 0. Then you get 0 divided by 0. But anyway, when you do that, you get a number. And you'll see that this number is small, 0.001432. And that's it. Now you just add them together. So the integral you want is, just repeating the slide, is of course exactly equal to the sum of this gx integral plus the correction, which was the polynomial divided by the singularity. And we just did this one exactly. There are no errors in this. You see that, right? It's perfect. Don't mix it up with the fact that I truncated. There's, of course, a significant error in this because I compared to the true integral, because I cut off the Taylor. I replaced sign by P4, right? But this is an exact evaluation of P4 over the singularity. There are no issues here. No numerics, nothing, right? The numeric comes here. This is not perfect. Why? Because of Simpson. Simpson is not perfect. It's a difficult integral. But the good news is that it's small. It's just a little correction. Most of the work was done by the and in fact, the singularity, the issue was done by that function. Anyway, you just plug this together, and you'll see indeed that it's very close to our first value. But likely all these digits are correct now, I think. Isn't that nice? So it's a trick, as I said. What if the singularity is at the right endpoint? I hope you all feel that, as annoying as it might be, it's completely trivial, exactly the same. Okay? I just assumed it was on the left endpoint. We had the Taylor about A. Of course, if you want to redo all this, you could do that. You would have to do the Taylor about. I mean, I guess the setting here is that you replace this by x minus 1, right? That's something you could do. And then you would get the singularity at the right endpoint instead. Or why don't you go from minus 1 to 0? Whatever you do, right? But you got a Taylor about now the right endpoint. A nice little trick you could do is to just put a negative sign on everything, and then suddenly you just switch it so it now is the left endpoint, and you can just use the formulas as they are before. What I'm saying is that if you're integrating from 0 to 1, and there's a singularity at 1, if you just mirror the whole equation by putting negative signs on the integration interval and the integration argument, the z, of course, you will now go from minus 1 to 1, and the singularity will be at minus 1. So this is not big magic, but it's a nice trick that I think makes it maybe easier to solve the problems. What if you have what if you have a function from 0 to 1? It blows up at both ends. What did we do at calculus? In order to even define that it works out, we had to split it up, right? In fact, it's one of those classical things that I try to trick the 1B students into, in treating these at the same, and there's a cancellation going on when it's in fact not convergent. But you got to split it up into one part that has a singularity at one endpoint plus another part with a singularity at the other endpoint. Okay? But from this point of view, it's of course obvious, right? The hard part was what we did before here. If you can do that, you can patch it together to do all these different cases. I don't even remember what exactly problems I assigned for you guys. Probably something similar to this problem. Maybe I used this right or double singularities. I definitely did some of this, though. The other type of improper integral. It's not blowing up now, so it's a nice function. But I'm integrating to infinity. And just to remind you of what calculus says then, so typically you have you start somewhere, not at 0, but you go all the way to infinity, OK? And you have 1 over x to the p. And it's easy to see by just integrating this that p now has to be greater than 1. OK? What do we do? As I told you, just numerically, you can think about going to infinity. And you can think about various little nice things that might be good enough. And one obvious one, as I said, might be to say, look, 1 over t to the p, x to the p is really large when x is 100. So why don't we just approximate that integral by going from 1 to a to 100 instead? OK, you could do that, and it might be good. And you could, if it's not good enough, you go to 1,000, right? Well, that's OK, but we like to promote good and better and more efficient methods. And we can, of course, do much better. In fact, you would have to waste, I think, a lot of resolution for composite Simpson to go all the way to 100, even if you do adaptive. So I just want you to think that it's not, you could come up with solutions to this, but the ones proposed here is a little trickier and nice. Now, it's actually quite easy, given that we just did this type of singularity, because you can go back and forth between these. You do a change of variable of basically just 1 over x. And then you're not integrating to infinity any longer, right? In fact, you're integrating from 0 to some value, to 1 over a. So you're not, now it's a bounded interval. But what will happen, of course, now instead the function is blowing up at one of the endpoints, which is fine because that's what we just did. So the answer to this type of problem is just do a change of variable, and then you're back to this. In fact, this whole section is based on this trick, and then various tricks to turn everything into this trick. Suppose it's at the right endpoint instead, well, just mirror. Suppose you have 2, patch them up. Suppose you go to infinity, do a change of variable. Let's look at the details. This is just calculus. If you do t equals 1 over x, you get a dt that is minus 1 over x squared dx. And you get these relationships here. You plug in the endpoints. As I said, a becomes 1 over a, infinity becomes a 0. And you get this extra t square factor. So actually you get some new type of form here. But of course, what we're interested in is not integrating 1 over x squared, right? Or xp. That would be boring, then you just do it like I started off with square root. Then you just do it with calculus. So what's the more interesting way? Well, the interesting thing here would be to have an f of x that is somehow well behaved. OK? So this we cannot do with calculus easily. And it goes to infinity. And what do we do? And well, the answer is you apply this transformation. Every time you see an x, it becomes a 1 over t. So this could be any function. You just replace it by 1 over t. You get this 1 over t squared y because of the dt and dx transformation, right? But the big goal was to change the limits of integration to something that we like. And now you moved this infinity to a singularity at 0. Singularity because t is blowing up here. And it might be that your f is so nice that that doesn't, but likely it will have a singularity there and you need to address it. I'll do a short example. Going to need a new blackboard. Too few blackboards here. So if you want to go from, let's see, 1 to infinity of 1 over x squared plus 9. Why is this a bad example? Because you know how to do it manually. You can squeeze an arctan out of this and take limits and stuff, I think. So, but let's pretend not, right? This is a function that is so difficult. Remember, most things you don't know how to integrate. So even if you accidentally can do it here, don't give up on numerics. Everything in the world is done numerically because you can't integrate anything. Exactly, except our made-up examples. So how would we do it using this trick? Well, as I said, we don't know how to do this. We had a trick so we got to do the change of variable. So the change of variable would be t is equal to 1 over x. Let's just rederive it from scratch. dx is equal to minus 1 over t squared dt. OK? As I said, x is equal to 1 becomes 1 over 1, so it's still 1. But the infinity is matched to 0, so now this integral becomes from 1 to infinity of 1 over x squared plus 9 dx becomes an integral from 1 to 0 of 1 over t squared plus 9. But then there is the dt, dx, that is minus 1 over t squared dt. All right, and then you just keep on going. And I guess actually we could have used the formula here at the bottom, which tells us that we can actually remove that minus sign and flip the integration limits, right? So we get them in the right order. So now it's from 0 to 1. And if you simplify a little bit there, you see that you now got 1 over 1 plus 9t squared dt. All right? And now what? Well, this was too simple example, because now it's all done. So we can still pretend that we don't know what arctan is, and then we do composite Simpson here. And I'm not even going to do it. You get some number. 0.411264.9. But in general, of course, I don't care what this is. In general, there will be some sort of singularity of something blowing up as it goes to 0, and you just apply the techniques from before. And I think the problem you got in your homework will force you to first do this, and then do what we did before. So bad example, because we kind of know how to do both that and that directly. The only big thing was that we went from the infinite integration limits to finite. So that's kind of the whole essence of this chapter. I did assign a fun homework, though, that is not at all, or two nice homeworks, where they did something different. And you remember the Gaussian quadrature that we like so much, or I like it so much, at least. It's it went from -1 to 1, right? Turns out that you can come up with all type of things, including things that go from 1 to infinity, at least if the function has a special form. And I wish I don't have the book here. I can't bring up the exercise, and I don't have it in my slides. But in your exercise, you have a problem where you ask to find something called Laguerre quadrature, where you actually find a specialized Gaussian quadrature formula for functions that are integrated all the way to infinity. But they have to be of the form e to the minus x times a function. Okay? And they show up a lot in reality. So this is a really practical thing. And there are two parts of it. One is that you should prove that it works. The other one is that you should use it, and then you can use actually a function I posted here. So I made a function for you in MATLAB called Laguerre quad. When you read that exercise, you can look at this function. If you, if you can solve it without this function, that would be great. But you don't have to go that far. I just want you to try it out. So I want you to prove that it works, which is exercise number 6. I'm talking about 4.9.6. And then I also assigned 4.9.9, where you're supposed to use it, and then you're welcome to use this function. You don't have to figure out roots of Legendre. I'm saying Legendre, Laguerre polynomials. Okay? This is just like with Legendre. I don't expect you guys to know that too much. It's actually almost, if you look at how to teach this stuff, you would like to teach, I think it's chapter 8 of this book first. It's called approximation theory. I mean, we're not going to cover 8 at all, but in 128b we do. You'd like to, first we should teach you guys how to approximate function by polynomials, then you would learn everything about Legendre and Laguerre, etc., and then we would use it, right? But somehow we decided, and maybe I agree, that quadrature is more important for you guys, so we put that in the advanced course instead. So you're not supposed to know about those polynomials. You can use this function just to solve that problem. So it's just to show yet one example of how to do this infinite integrals. But I know you've seen in the applied sciences that people integrate things to infinity a lot in physics and engineering, or you have singularity. So this is kind of an important topic. And these are just some of the tricks you can do. That's all of chapter 4. All right? So a lot of quadrature. I think I told you before that in everything we've done so far, and also some of these 128b topics that we're not going to do, they are considered kind of introductory or undergrad numerical analysis, in the sense that everybody's supposed to know it. When you go into, if you really like this topic and want to keep on going, we have, in the math department, we have 3 graduate courses on numerics. And they are not on quadrature or splines or solving equations or anything like that, because you're expected to know it when you come into grad school doing numerics. That's undergrad numerics. What is graduate numerics? What is that we focus all our attention on? Well, I just mentioned, it's chapter 5, it's differential equations, because that's what they want to solve in the real world. And it's also one more thing, linear algebra, which is chapter 6. So I'm saying that just to tell you that the end of the course now is going to be just a glimpse into what really is the big research, or the big research topics here. Everything you learned so far is more traditional. It's super important. Everybody's supposed to know how to fit polynomials, integrate things, solve equations. We do all the time. But the real reason we're doing it is to solve differential equations and large systems of equations, linear systems. So that's why we're going to this, and I'll bring up a new set of slides, chapter 5. This is, let's see how this is split up. First, I have a little section called elementary theory. If anyone by chance have taken 123, I don't think, but I think some of you might. Some have, okay. Then this is trivial. Clearly, before we start solving differential equations, maybe we need to know a little bit about them. This is not what most of the chapter is going to be like, and it's just a little bit of best off, the quick crash course version of 123 to know a little bit when we can solve these equations. Pretty quickly, we'll start talking about actual methods. And actually, each chapter here is a new method. Methods. All these are new methods. And at the end, we talk about some very important concepts. But we'll just discuss a lot of methods that people have proposed. And you might ask, why do you need to know them all? In fact, you could go back to what we've done so far. Why do you need to know Gaussian quadrature, composite Simpson, composite trapezoid? And the answer is that some are useful for some things and also to get perspective and to understand it. But in this case, it's really that all these methods are used all the time in different scenarios. So you certainly want to see it. But having said all that, we're going to start with just some theory of initial value problems. I, of course, expect you guys to know what an initial value problem is. Oops, I would like to put one up. Well, we'll come to that. Let's start with something that is not the actual thing we want to solve. Have you heard about Lipschitz continuity? So in 123, you hear about it a lot. But I don't think it's mentioned much in other. It's really a numerical concept. So you should know what continuity is. And you definitely know what differentiability is. And Lipschitz continuity is right in between. And the definition is here. That a function is satisfying a Lipschitz condition if, and there is a condition, and it's a little bit complicated here, and I'll tell you why it's complicated. They want to get you guys prepared for what's coming, namely solving ODEs. So that's going to be a function f that takes two variables, time and the function value y. Okay? So they introduced this. I think it's going a little too fast. I would just say, look, any function, let's say it just depends on one variable, has a Lipschitz condition, or is Lipschitz continuous, if you have this condition that if you do f of y1 minus f of y2, just pretend the t is not there, it's bounded by a constant times the jump in the y's. Okay? And it's kind of new. You might think about it. You might think this is continuity. You might think it's differentiability. And it's related, but it's neither of those. It's something right in between. This turns out to be the most important condition for saying something about differential equation. It's exactly the right condition you want on a differential equation to be on an initial value problem to have unique solutions, which is what we're going to look for. So anyway, so let's just talk a little bit about this. So I would say, if we summarize the different levels of continuity that we have, you all know that continuity is a fairly fundamental concept. What does it say? It says that if you take an f, maybe I should call it y1. I'm going to call it x and y because that's typically used. And you look at the difference between the function at two different points. As those points get closer and closer, this jump has to go to 0. As well, in whatever way you want, these points get closer and closer. Okay? So there are other ways to formulate this. Of course, you could be standing at a point still and have another point getting closer and closer. But regardless of what you do, it has to go to 0. And you might want to think about functions that are not continuous, which include, of course, a function like a step. The Heaviside step function, you all know about that. Why is that not continuous? Well, to begin with, it's a little iffy to just say the Heaviside step functions. You all know it's 0, and then it becomes 1. Well, to define it, I have to say what it's at 0, right? But let's just say something. Let's say it's 0 at 0. So it's 0 inclusive, and then it's 1 not inclusive all the way to the rest, right? That's not a continuous function. And why is it not? Because clearly this is true almost everywhere, except that if you stand right at 0, let's say y is equal to 0, and x is approaching, to begin with, from the left, right? Then it's actually fine. Because then you have 0 minus 0, it's all going to be 0. But if x is approaching from the right, coming from positive values, you have a jump of 1. No matter how close you get, it's going to have a jump of 1, right? So that's continuity. Anyway, just a little review of that. Here comes this Lipschitz continuity, which says something slightly different. It says that it should be bounded in the following way. Less than or equal to some number lambda times, let me call it L, since it's L there, L times x minus y. I don't want to change too many things. Okay? And there, I don't need a limit here. This is always true. Let me just say what I did that is not done up there. My f here is only a function of one variable, OK? The t there is just a dummy variable that will make sense when we do differential equations. But to talk about Lipschitz continuity, don't need that, OK? You just have a function. And just like here we plugged in an x and a y, you can do that here too. And we want to say something about this jump in f. And what I'm saying is that it's bounded by some constant L times the jump in function values. OK? And you can think a little bit about if this is identical to that. Well, I already hinted that it's not. Does it imply that? Is this more general or more specific? Is this a stricter condition? The third type is differentiability, which also has these numbers in there. We could say something like f of x minus f of y. And I'm going to do absolute values here. X minus y. Well, it goes to a number that we call the derivative as x minus y goes to 0. So this you, of course, are familiar with as well. And if this limit doesn't exist, it's not differentiable. So you can come up with examples of functions that are all of these. But I'm going to show you some specific cases. Let's just look at these expressions a little bit. So this one is to get close. When we look at the actual example, it's kind of nice. I think you know that differentiability is a stronger condition than continuity. If you have a function that is differentiable, it really means that the derivative is not making kinks, right? It's smooth. Smooth is another word, actually, for at least higher order differentiability. You know that it has to be continuous. OK? So this is much stricter. And of course, the way I wrote it, you could guess that this is right in between. OK? To see that, it's pretty clear that this implies that. If I tell you this, you can just let x minus y go to 0, and you get a constant L times 0 is bounding the jump in f, which gives continuity. So clearly 2 implies 1. OK? So it's stricter than 1. And you might want to think about which type of functions would be 1 but not 2. Are they identical, or can I come up with something here? The issue is kind of in this constant. And here's the typical example of a function that is 1 but not the other. I guess this is a case when you need color, because I want to draw a function that's coming here at 0. All right, how about that function? So it's f of x equals basically square root of x if x is positive, but otherwise it's 0. OK? So it's square root of x, but I'm extending it to live well beyond 0 here, all the way for negative numbers equal to 0. All right, what is it? What is it not? Is it continuous? I think you all have an intuitive feeling. Don't they have rules in Math 1A or something that if you can draw it without lifting your pen or something, right? Another word is that, you see there's a huge issue here. There's like a kink here in the derivative. That's not the only issue. The issue is actually that we have an infinite slope here. And we'll come to that. But it's certainly continuous. If you want to look at the condition, give me any x, y, and shrink, and they will converge to the same number, which is another way of saying that the jump in fx and fy is going to 0, right? So it's certainly one continuity check. You all know that it's not 3, right? Well, it's 3 everywhere, but not at 0. And one way to see it is that it's making this kink, so that it would be hard to define a derivative there. Also, that derivative would not be a number. If you look at the expression for the derivative of square root, it's actually going to infinity. So we all know that differentiability is not the case, for whatever reason you want to convince yourself. How about 2? Is it Lipschitz continuous? Can I bound the jump in the function value by any constant times the jump in the x and y values? And clearly this is the case everywhere. 0 is the issue. So let's pretend y is 0 to make all this simpler. Then it's really simple. Can I bound the function value by a constant times x? So you have a little epsilon. So you put y right here, and you have your x there. Okay? And you let x get closer and closer. Let's say x is equal to epsilon. Okay? The problem is that this number then is epsilon, while this is just square root of epsilon. Can you bound square root of epsilon by a constant times epsilon? That constant would have to depend on epsilon, which goes to 0. That's not a constant. Another word, a better way I think to see it is that clearly this constant here sounds like a slope. It sounds like I'm trying to, if you have a jump in x and y, I want to bound how much the function can jump. Do you all see that this L is an upper bound on the slope of your curve? It's hard for me, if I draw a curve that is never more than L slope, then this is going to be satisfied. And that's a theorem coming up. Now, here's an infinite slope at that point, which means that as you get closer and closer to that point, you can make a little step in x and y, and you make it does go to 0 though, so it's right in between. But you make a substantially larger jump in the function value. It's a little tricky, but it's not Lipschitz. So there's one example, and then another way to see it is that yeah, it's really close to continuity, right? It's the only issue that happened was that we got this infinite slope. Let me show you another case. Here's another example. This is a typical example of something that is Lipschitz. Absolute value of x. Clearly continuous. Nu it. Differentiability. Clearly not differentiable, right? In fact, if you want to do, I don't know if you saw those right and left derivatives. If you're standing at 0 here, you can define a derivative just looking to the right. And it's plus 1. If you're just looking to the left, you could imagine this limit coming from the left and giving you a slope looking to the left of minus 1. But differentiability is defined to say that these limits must exist and be equal for any direction of how you approach this. So in other ways, you cannot really define a derivative at that point. It's not differentiable. In terms of my expression, this limit would, well, I guess because I took absolute value, they would both go to 1. But you know, then I could just make a slightly different slope, and the limit would not exist. So that's not cool. How about Lipschitz? Can you tell me that if you tell me an x and a y, maybe you want to put 1 at 0, but we don't have to. If you give me an x and y, can you tell me that the jump in fx and fy is less than a constant L times x minus y? It seems hard for this function to run away very far, right? I mean, if you're standing, it's continuous. So if x is equal to y, they are equal. Now they drift away a little bit, and the functions might drift away, right? But they're not going to go very far. That's what Lipschitz is. In fact, it is Lipschitz with L is equal to, do you have a good L for me? 1 works. You might have to think about it. In fact, it's 1 almost anywhere. Suppose x is here. I mean, that's a line with slope 1, right? If x and y go away from each other, the function values go away exactly the same amount, right? So 1 works fine. If I turn it into 2, it would be 2. That constant doesn't matter, right? Now, you might want to think what happens when x is over here. Well, then it's just better. The functions actually go not as far apart. So that works fine. So that's kind of interesting. These are typical examples. And we'll come back when we see some theorems about differential equations to see how this matters. Yeah?
How is this related to uniform continuity?
Uniform continuity. That's when you look at the entire function, right? And you have functions that every subsequence has to converge to the same point. This does not necessarily imply that, I think, if I remember it correctly. But I have to check that. I haven't taught 104 in a long time. But you're right. That's beyond just this strict condition, because you have all the sequences converging as well. Good question. Not sure. Yeah.
Just out of curiosity, would the step function be not continuous but Lipschitz?
No, these are all strictly more selective.
Yeah, but wouldn't you be able to bound the step function by L?
You can bind the jump by 1. Okay? But if you let this go to 0, you need to multiply by more and more here to bound it by 1, right? So it's not about bounding the jump. It's about bounding the what I call the slope, namely the jump as related to the change in x and y. So that's good to think about. But yeah, the case is you take y at 0 and x at epsilon, right? Then this is epsilon. And this is, as you said, bounded by 1. But that means L is 1 over epsilon. And that's not cool. That's not a constant. All right? Let me bring up the slides to see what theorem we're now interested in. And just to connect to this again, this is what I talked about. But they decided to have a function that has 2 arguments, a t and a y, because that's what we're going to have soon. And it's actually quite confusing. But it's completely analogous, just ignoring the t. The t is not the issue. So they say that now it's Lipschitz continues in the variable y in the second argument, right? And everything is the same. You can also define exactly where, what type of variables this is the case for. And if you have 2 variables, of course, it becomes R2, etc. Not that important. But maybe I should mention here that what I did here, my examples, I imagine the domain to be everything, the entire real axis, right? You can actually think about, let's say x2, x square. Is x square Lipschitz continuous on the entire real axis? So the way to think about this is actually a little difficult. But you would have to look at this. X squared seems like a very nice and well-behaved function. But remember, I said it's kind of bounding the slope. So if you want to start, so more examples here. F of x equals x is, of course, Lipschitz with, for example, L is equal to 1, right? 2x is, of course, the same with L equals 2, right? No problem. How about x squared? You got to give me a constant such that for any x and y's, you can guarantee that, again, the slope is really not, it doesn't have to be a well-defined slope, but the jump in f's is not more than jump in x. The point I'm trying to make is that if you let me go to as far as I want, you cannot really give me a constant. Because I can always go further to the right, and the slope will be more and more, right? So this is really not Lipschitz on all of R, okay? But of course, to rescue this, you would just limit it and say that what if I'm just between 0 and 1, and then you'll be fine. Yeah?
Would you then say it's no longer differentiable?
What?
Would you then say it's not differentiable on R?
In that sense, what I said here is not entirely true. You're right. It's not boundedly differentiable in the sense that the derivative of x squared is 2x. And it goes to infinity as you go to infinity, right? So yeah, you can define it for any finite value. OK, so let me say it like this. On any interval you give me, let's say you want to go up to 10 million, right? It's Lipschitz, it's differential, everything is cool, right? But Lipschitz insists on finding that constant. So if you strictly want to make this a stronger condition than that, I would have to use this mu and say that for any number you have finite. So it would be bounded differentiability. That's a good clarification, because clearly it's a differentiable function. But the derivatives go to infinity. Anyway, in practice, we don't like infinity for any practical applications or any numerics, definitely not, right? So we like to cut things off. And what you do is just to say, I'm not going to work on all of R. I'm just going to say, look, I'm just going to consider values between 0 and 10 or something. And then many of these issues go away. And we'll see what this, in fact, they do use convex, but you know what a convex region here is. Here comes a nice follow-up to what we discussed. The theorem up there, I think I actually asked you to prove, fairly straightforward, that says that if you are differentiable, that, of course, does imply the Lipschitz continuity, and you can choose the L to be what? The derivative, or bound on the derivative, the largest possible derivative. That's kind of nice. So suppose you have this function, and the derivative, remember here they do partial derivatives with respect to y. We would just say f prime in my case, with one variable. The derivative is never greater than L, then it's also Lipschitz continuous, with the Lipschitz constant being L. So that's kind of nice. And in fact, of course, in all our little silly examples we're doing, we always have cos and sine and t times cos, etc. Right? They are all differentiable. So in practice, in numerics, we actually have a lot of differentiability. So this is, if you want the Lipschitz constant, this is likely the way to go. You cannot apply it here. You can kind of apply it here to realize that it's going to be difficult, because the derivative of square root of x is 1 over 2 square root of x. So you kind of have an infinite derivative, and you will see that there are some issues. But the theorem tells you that if you have a bounded derivative, that's the Lipschitz constant. Anyway, so now comes the main reason. Why are we doing this? And the answer is this theorem. We're trying to solve initial value problems. Initial value problems can be stated as follows. So this is a lot of review of, this is Math 1B, and I know you solved a lot of stuff in 54 as well. But just reminding you that we have a form, and we like to write it on the form that we have really just one independent variable, okay? And we call it t or x. We will go back and forth between that. But it's often t, and you know why. Because the whole concept with initial value is that you start at the time and go forward. It's not at all necessary, but it's just a nice convention because so many applications are based on time. So you have y prime with respect to this t equals to whatever you want. And whatever you want could be t. What if it's just equal to t? Do you call that a differential equation? It kind of is, I think. But it's not very interesting because it's just quadrature, right? So to make it interesting, you want it to depend on the function y. And it becomes a differential equation. This t, by being an initial value, you give conditions on the solution at the typically left endpoint. And how many conditions do you need? The way I wrote it here. Then the order of the equation, right? So there's just one derivative. It's a first order differential equation. You need one condition. So you tell me what y is at point A, whatever number alpha you want. And now you ask me, what is it equal to at B? We often use the term, we're going to integrate this in time from A to B to figure out what happens at B. And if you want examples, just go back to any Math 1B thing. But of course, in the problem set 3 is kind of fun. You're going to do pendulums. Imagine you're taking a spring and it starts oscillating. And I'm telling you where everything is, and you're going to integrate it in time. What about this domain? We kind of need to bound things off here. And in general, we're going to do here to say that the time cannot be just anything, because there's no reason. You're integrating from A to B, and you will never, ever consider f at any times less than A and greater than B. So we define this strip, this semi-infinite, or this infinite strip of values in ty space. And y could be anything, but sometimes, as I said, you have to cut off y as well in order to make this well specified. So here what we do. Basically, it's saying that if f is Lipschitz in the y argument, you have a unique solution. Okay? Do you know why we want a statement saying unique solutions? It's in math, you might sometimes wonder why we care about proving without actually getting. Solving, I think, is clear to you. We want to solve equations because you want to use them for something. Why do we want to show that a solution exists and that it has a unique solution? Unique is stronger than exist, right? Exist means that, and in fact, I don't have the theorem for existence, but you could go a little, in fact, if you just impose continuity, you have existence. So if you take away Lipschitz, and in fact, we can look at this function here that was continuous but not Lipschitz, you have existence. So there are solutions. The problem is there might be many. Why is that a problem, especially for any applied science or for numerical analysis? Yeah. Yeah, that's exactly right. Yeah, you know, we love to have our, like, we talk about errors, and I want to make statements saying that our numerical method will give you the solution. And so far, we just said the true solution. I don't think I ever said one true solution, right? We compute integrals, we solve equations. In fact, solving equations was an issue because there could be many solutions, right? But then we have to say there is one root, etc. But what if there are many solutions? How could I possibly say that the error goes to 0? Well, I could maybe say it goes to 1 of the 0, but you can't have a lot of solutions. So this is really what you want to do. It's not that much a practical problem, at least not in these exercises that we're going to do, because things are going to be super Lipschitz continuous. It's going to be differentiable to high order, etc. But it's good to know that really exactly the condition you need is going to be Lipschitz to get uniqueness here. Let me show you 2 examples on things on differential equations here. So for the uniqueness of those, we're going to use these. So let's keep them. Go over here. So I'm kind of exactly going to use, let's do this one. Well, let's start with uniqueness. Let's start with something that is not bounded. So I'm setting this f of t comma y equals to y squared. OK? And of course, we always need an initial condition, but it's not that important. Y of 0 equals y0. That's just a number. I could set it to 1 for the argument here. It doesn't really matter. Now, I did mention without having a theorem that you actually just have to look at continuity to see, or bounded continuity, if it can be bounded. But Lipschitz, if we look at the Lipschitz here, we have that we need to find this constant L to bound the jump in f from the jump in x minus y. And in fact, it's exactly the example I had before that I just erased with the x squared. Because remember, I kind of renamed x, y, and made it the second argument. So regardless of how you see it, I cannot choose that L, because it just gets bigger and bigger. OK? If you promise me that y will never be too large, I can give you an L. But that's an issue. Then the theorem wouldn't apply as it is right now, because it says that you have to do it for all y. And in fact, there are more specialized forms of this theorem that tells you that this region here, you're putting bounds on y. But in general, that's not necessarily the case. All we can say right now is that it's not really Lipschitz. And if you want to be careful here, you want to say in y, right? But that's almost understood. At least not on all of the real x. So what does that imply? It says we don't have uniqueness. In fact, we don't even have existence, depending on B. But this is a pretty strong condition. There are very few conditions on B, right? So how do we analyze this? Well, the good news is that you can solve this exactly. Remember how to solve this with Math 1B techniques? It's nonlinear, so most of the techniques you learned in Math 1B would not apply. But there was one very cool technique that we could solve a lot of special nonlinear equations with. Separable, right? Separation of variables. Just divide down this, write y prime equals dy dt. You divide down the y and integrate both sides. So super easy, you can get the solution to be y of t. And if you plug in the initial condition, you see that it's actually 1 over y0, the initial condition, minus t. OK, so what's the problem with that? Let's draw it. T, y. And it starts at 1 over, no, it starts at y0. Right? And clearly, it seems to increase as you start moving. And it's going to come to a point when t is equal to 1 over y0 when it goes to infinity. So that's the solution. Why is that bad? It's not necessarily bad. We don't have these things in nature, really, that often. It's kind of an explosion. Our model is breaking apart. If this was modeling something in nature, most likely it's an approximate model that doesn't take into account that when y becomes really large, something else happens, right? So, but that's fine. You could have this equation. But clearly, I cannot say that it has a unique solution, because that would imply existence. And I have no way to say, if you put b over here, that I can define the value. So you might argue that if I put b over here, I'm fine. And you would be right. It's just not covered by the theorem, which tries to tell you that for any b, it will exist. All right, so that's the first case to think of. By the way, maybe I should have started slower. What if you remove the square? Let's just do it by thinking about it. That's the model problem that I'm going to use all the time, of course, because I like e to the x, e to the t. And if you replace that by y only, it's e to the t. How would this change? Clearly, then you know that it's nice. You know the solution is well-defined for any b's you might come up with. And indeed, then the derivative here is 1. Then it becomes Lipschitz with L equals to 1, right? Isn't that amazing? Just putting a square there just completely changes things. And it blows up and doesn't exist beyond a certain time. So maybe I should have started with a y to be the easier example. Now let's do the square root. That's kind of nice. It was not completely Lipschitz. And we'll see what the issue is there. So let's do, I think it's nice for the numbers to put a 2 there. And let's start at 0. You have to start at 0, otherwise you avoid the problem. I don't want to avoid the problem. I want to step right into the problem. OK, so the theory is telling us that this is not going to work out so well. We can't find that constant. Whatever way you want to see it, you can also look at these slopes. But it's certainly not Lipschitz everywhere. And you might have to ask yourself, do you need to worry about 0? And as I said, if you start away from 0 and can tell me that you will never go to 0, then you can formulate a new theorem that tells you that everything is fine. So things are not hopeless, right? It's just that this theorem is a little more blunt, saying that you've got to show this for all the y's. So what does that mean? Is it bad? Well, here are some solutions. You do have solutions, actually. But many of them. So here's one. Do you have a solution for me? Remember, we're solving y prime equals 2 squared of y. You have a very easy solution for me, starting at 0. 0. That's the one I'm looking at. So that's a good one, right? Remember, we're solving y prime equals f of t comma y, which is 2 to the square root of y. Starting at 0, of course, 0 everywhere is fine. So that's a great solution. The problem is that here's another one, t square, I think. T square, if you differentiate that, you get 2t. OK? And you get 2t here as well. So that works. It starts at 0, too. So drawing these, I have two solutions. One that stays, as soon as you're drawing an axis, you need color. Here's one solution. Here's another one. Actually, I should not draw to the left. OK? We start at 0. But there are two different solutions. And that was a really bad curve because it looks like it has a slope. It's x squared. And it's t. Are there other ones? You can actually mix them. You can go a little bit with 0 here, and you're all good and happy. And then suddenly you decide to take off with a parabola. Just looking at the slopes, that seems to be fine. You could write it as 0 if t is less than a constant, and t minus a square after that. But it doesn't really matter. I'm just telling you that there are lots of solutions. So, summarizing all this, you really don't want the derivatives of your f's to blow up. If you want existence, you can't even allow them to blow up as you go to infinity, because you could have a function that wants to go into infinity, and it will just keep on going, and you might not survive to your intended b value. That's what this theorem is trying to say. Good, nice, well-behaved functions, like in your program assignment, they have these f's being things that stay well-bounded. They also introduce a concept called well-postedness. And let me just quickly go through it. What this is all about is a little technical. And what it's basically saying is important for numerical analysis, but we won't use it very much. It's saying that you have a differential equation. I wrote it here again. And you want to be able to say that it's well-posed. And what it means, kind of in words, is that if you perturb it a little bit, the solution won't drastically go somewhere else, in the sense that you can bound how far the solution gets if you perturb it a little bit. Suppose you take any differential equation like this one, right? If I add plus epsilon here, what's going to happen? Actually, this is a bad example because it was not Lipschitz, so I cannot apply the theorem. But suppose you have a nice differential equation, and you put an epsilon here. What will happen to the equation? Well, it will give a different result, right? But what this is trying to say is that it's not that far away, in the sense that it actually scales linearly with that epsilon. In the same sense, you might want to perturb the initial value. I started at 0 here and pretend that this was a nice equation. What if you start at, they perturb the initial condition by delta. Oh, it's all deltas, by delta 0. How bad is that? Again, it's fine. It's going to be a different solution, but it's going to perturb in a reasonable way. That's what all this is about. So if you look at it, that if you tell me a delta, you see what I'm doing? I'm taking the equation and adding delta. and I'm changing the initial condition. I'm getting a new solution, let's call it z instead of y, and the theorem is saying that well post means that these two are not more than a linear a constant times epsilon away from each other, where epsilon is bounding these deltas. Okay? It's a little deep. Clearly, you're getting a different solution if you're changing the equation. It's just saying that it can't, and that k, that constant k could be anything. So I'm not saying that it's small. It could be that you perturb 10 to the minus 6, and the error is huge, right? That would mean you have a big constant. But what does matter is that it scales linearly with epsilon. So if I perturb it half as much, the new solution z should be half as far away. Okay? Why do I care about a theorem like this in numerical analysis? Do I have errors? We're going to be making errors all the time. And if the theory tells you that, look, I have an equation here, it's all good and it's perfect if you solve it exactly. But if you go a little bit away, it breaks, things go really bad, right? That's just not going to work. So you need a well-posed problem before you try to solve it numerically. And it's just the general idea of perturbations and what it means. So basically, if you're trying to integrate something, and there are equations, actually most things in real life are well-posed. It's just that that k could be extremely huge. You can imagine having an electron going through some system at some high speed and being extremely slow. And if it just goes tiny little piece apart, it's going to deviate and blow up. Okay? It's actually still well-posed. It's just that I'm talking about very large constants. But what would never work is if it's such well-posed that that deviation, if you go epsilon away, it's going, let's say, square root of epsilon. If you start epsilon away from where you want it to start, the actual trajectory goes like square root of epsilon. That would be bad. So that's well-posedness. And of course, the theorem is telling you, if you're Lipschitz, then you're well-posed. That's kind of all of the crash course 123 you're going to get to. This is not to say that you don't need to take 123. This is just what we need for numerics. Lipschitz is the concept. It's actually not that practical for most of what we're going to do because we're going to be well beyond Lipschitz. We're going to have cos t and cos y, very nice, well-behaved things. But the theory tells you that Lipschitz is the condition that gives you both uniqueness of solution and this concept of well-posedness. Let me say a few words about Euler's method. I expect you guys to kind of have seen this before. We definitely teach it in Math 1b and in maybe in other places. It's the simplest method, I think, for solving a differential equation numerically. It's based on the very simple idea of just looking at this equation. You know, a differential equation written on this form is so nice because it really just tells you what the derivative is. So if you write y prime equals f of t comma y, and you tell me where to start, and many times, I often put this starting time at 0. You all see that it doesn't really matter. Maybe you could put it at a instead. But what is the method? What is the differential equation saying? You're standing here, and you want to predict the future. It's an initial value problem, so you tell me what its value is at starting, and you want to tell me, and you want to solve it and tell me what it's later. You're telling me for any value of t comma y. Remember, this is t, and this is y. You tell me the slope. So the way to do this is, of course, to say that there's a slope there. Okay? So the solution will initially have this slope exactly, otherwise you did something wrong. But then, of course, as you start moving away, f likely changes, unless you have a very simple problem. And then the slope changes. And in general, you get some interesting solution. And the true solution is called y of t, right? So that's what a differential equation is. This is a whole t comma y space of slopes. And by picking a starting point, you can trace out one particular. And at every point, of course, here, the slope is equal to f at t comma y for this particular point. F is the slope. I will often call f the slope, because that's how the problem is defined, slope of the solution. And it's not unique, of course. If you start somewhere else, it will be another solution. But with Lipschitz and everything, you'll be fine. So what is an obvious numerical method for doing this? Well, I started off here, right? I told you the slope at this point. Suppose it doesn't change. The true solution is in a straight line. Then I just take a step. Or in words, I'm going to introduce a delta t. And we're often going to call it h. OK? Let me call it h. Sorry, this is PD language. I introduce a step size h. And clearly, taking this slope, I could predict this new value there by simply doing what? y0 plus h times the slope, right? Okay? Now, that's not correct. The true solution is here, and I got there. I'm making an error. This is a numerical method. Hopefully, we should be able to say that if h shrinks, it's going to get better. That would be great. And we will say that. We need some notation. Let's look at the notation in the slides first. These points we're going to call t with an index. It's almost exactly like in the quadrature part. So if you start at t0, then you get at t1, and of course there's going to be a t2. What do you do next, by the way? Well, at that point, you say that, look, I moved quite a bit, and the derivative has changed. Let's just stop and recompute the slope. And of course, likely now the slope is going to be this, or something else, right? And then you take a step of that. That is Euler's method. Very simple. And it's still wrong. So notation-wise, we have all these t's, and we have a step size. And I'm going to look at the derivation soon. Let me just write down the method. Didn't I just write out Euler's method? Let's just look here. We'll look at the derivation next time. But the method can be written like this. Why do I call it W? Because it's a new solution. And if I call it Y, it would be confusing. The Y is the true solution. And when you start doing numerical numbers, let's call it W. That's what they do in this book. It's somewhat unusual. So I started exactly at the alpha, which I called Y0, right? And you keep on adding h times the slope, and that's the method. I didn't even write you a MATLAB function for this because it's trivial. But of course, next time I'll show you how to solve a trivial equation, and you'll do something more complicated. And the big thing we're going to do in this section is actually to come up with a theorem proving, if we have time, that it works, which is what it's all about, saying that this is actually a really bad method, but it works, in the sense that it does give you the true solution eventually. So that's the setting. But you have a lot to start with all your homework in 4.9 and 5.1. So let's stop there. Thank you.